Okay, so we've looked at neutron porosity. We're now going to look at a tool which is almost always run in conjunction with the neutron porosity tool, and that is the density tool. Density tool is what we would probably regard as one of the most important measurements that we make on LWD or in any kind of formation evaluation. It really is an important measurement from the point of view of the petrophysical evaluation of the reservoir, and we go to a lot of trouble to try to get it right. So I'll show you how the tool works and some of the issues which you may see in the data. Now, from time to time, some of us may have encountered an angry customer. This is intended to represent an angry customer, and in particular an angry petrophysicist. And from time to time we may hear the angry petrophysicist say to us something along the lines of, your density is 0.05 grams per cc too high. Now, unless you fully understand the measurement, you might think that that really doesn't sound like a big deal. 0.05 grams per cc sounds like a pretty small amount, and you'd be tempted to wonder why this guy is getting so upset about this small, apparently small error in our measurement. So what I'll do next is to take you through the process that the petrophysicist goes through when he takes our data and uses it in his calculations to show you the impact that an error like that can have on his evaluation. So let's think about what the petrophysicist typically does with that information, with our density measurement. Let's take our error, our plus 0.05 grams per cc error, and we'll put that into this equation, which is a calculation of porosity. The density measurement is primarily used to calculate porosity. And you can calculate porosity using this equation where rho m is the matrix density of the formation, rho b is the bulk density, which is the actual measurement that we're making with the tool, and rho f is the fluid density of the fluid in the formation. So using this equation, we measure rho b, we can get a value for porosity. Now if we stick an error of plus 0.05 grams per cc into this rho b value, let's see what that does to the porosity. Well, what it does is it brings it down by 2.7 porosity units, or PU, which still doesn't sound like a lot. That's 2.7%. It's a pretty small error. So let's see what the petrophysicist will do next with that information. What he might do is use this equation. This is Archie's equation for water saturation. It has a number of different elements in it, which I've listed here on the right, with some nominal values just for the sake of this discussion. But the porosity value from the previous calculation goes into this equation. It goes in down here, and that's going to obviously have an impact on our calculated water saturation. The amount of impact is something around 2.5%. So what it's done is caused the water saturation to go up by 2.5%. So what that means is we have more water and less oil by about 2.5%. Okay, that still doesn't sound like a big deal, so what next? Well, we'll put the information that we have into this equation. This is calculation of oil in place. This is the total volume of oil in the reservoir. Now, this is one of the main functions of a petrophysicist, is to be able to come up with estimates of this. This essentially is the amount of reserves that the customer has at their disposal, which is going to have a direct impact on their profitability, on their share price and their stockholders, and so on. So it's a big deal to calculate this as accurately as possible. The way this is calculated is there's a constant which takes care of the units, the area times the thickness of the reservoir. In this case, with this constant, this is an area in acres and a thickness in feet. You'll find other versions of this equation which use different units for that. But area times thickness is the volume of the reservoir. Multiply that by 1 minus the water saturation, which is the oil saturation, and multiply that by the porosity. So that gives you the total volume of oil in place in the reservoir. And you'll notice that both the water saturation and the porosity come into this. So we'll see how that is impacted by these errors that we've introduced with our density measurement. The 2.5% increase in water saturation goes in here. The 2.7% decrease in porosity goes in here, so that kind of has a double effect on the result, which puts the estimated oil in place down by 22 million barrels, if we assume some numbers for the thickness of the reservoir over here, which at today's price, although as I speak the price is falling, let's assume a $70 per barrel oil price, that works out at something like $1.5 billion less in terms of reserves than the operator was expecting. So that could have a very significant impact on their business, on their shareholders, and have major knock-on impacts to their financial decisions. So that $1.5 billion came about due to what appeared to be a very small error in our density measurement. So this kind of explains why we take so much trouble with our density tool, why it's so complicated, and why we spend so much time and effort trying to get the density measurement right, because it really is a critical measurement from the customer's point of view. So let's look at the actual tool that does the measurement here. The main tool that we use today is the ALD, the azimuthal lithodensity tool. It has multiple functions. Its main function, of course, is to measure density, the formation density. It also produces something called the formation photoelectric factor, or the PE, which I'll explain a little bit later. And some of the tools also have an acoustic standoff sensor. So with that, we're able to provide estimates of the hole size and the hole shape. Now, all of those measurements come in 3 different variants, or 3 different flavors. We have a conventional, rapid sample, and azimuthal measurements. So you'll hear people talk about azimuthal density, rapid sample density, azimuthal PE, rapid sample PE, and so on. All of these things up here come in all of these different flavors down here. But the basic way that we calculate density, or PE, doesn't really change with these. This is just how we divide up the samples and how we represent the data from different parts of the borehole. Now, the tool is laid out as shown on the right. The tool has a stabilizer blade on it, which is a little bit smaller than the borehole, typically about 1/4 of an inch smaller. And in one of the blades of the stabilizer, we have some detectors. We have a detector here and a detector here. And up here we have a source. This is a gamma ray emitting source. This is screwed into the side of the tool, and gamma rays are emitted through a little window, which is just shown there, a little low density window which allows the gamma rays out into the formation. They bounce around, and some of them will make it back to the 2 detectors. And based on the number of gamma rays that come back, we make a count rate measurement from each detector. We can tell something about the density of the formation. This little piece down here is where the acoustic standoff sensor is, if the tool has it. The 4 3/4 inch tools, the smallest tools, do not have this, but the larger size tools do. That's not always present. It depends what type of tool you have. Okay, so I'm going to explain now the difference between the conventional and the rapid sample data. I mentioned that we have 3 flavors: conventional, rapid sample, and azimuthal data that come from this tool. The conventional data is the simplest to understand, so I'll go through that one first. Let's assume that we have a tool in a borehole which is nice and circular, and the detector is mounted in one of the blades of this 3-bladed stabilizer. What we're going to do is look at the count rate from that detector as the tool rotates to see what impact the rotation has on the measurement. And what we find is that since the distance between the detector and the formation is pretty much constant as the tool rotates around, there really isn't any variation to speak of in the count rate. We do see some statistical variation. We see, some samples are slightly higher than others. That's just due to statistical noise in the counts that we're picking up in the detector. That's nuclear statistics are always a little bit noisy like that. But on average, they produce a constant value, even though the tool is rotating around the borehole. The points, the little samples, these are count rate samples. Each one of these represents about 100 milliseconds of data. So we're sampling here over a period of maybe 10 seconds. So that might be 100 samples. Those samples form a distribution like this, to which you can fit a normal or Gaussian curve, and from that you can calculate the mean, and from the mean you can calculate the density of the formation. There's a direct relationship between count rate and density. So that's a simple case where we just take all the count rate samples that we have, average them together, and use them to calculate a density. Now, what happens when the borehole becomes enlarged? Here we've got a case where the borehole is not circular anymore, it's become slotted or elliptical. And let's look and see what happens to the count rate in the detector now when we rotate the tool. So we'll do the same thing again, and now we see that there's a very significant variation in count rate as the tool rotates. That as we see high standoff, large standoff above the tool, we also see high count rates. Whereas as the tool approaches the low side of the hole, we see low count rates. Now, if we just took the average of all of these, we'd get a value up here somewhere, which would be very different from what we had previously, and would clearly be wrong, because what we'll end up with is a measurement which is heavily dominated by the mud in the borehole, rather than the formation itself. So what we do in the tool is a trick with statistics to divide up this distribution into bins. We have what we call a low count rate bin and a high count rate bin. And a piece, sometimes we see a piece in the middle which basically gets ignored. What we're doing here effectively is isolating points in the low count rate bin which came from areas of the borehole where there was very little standoff between the detector and the formation. And that's what we want. If we use areas where there's a lot of standoff, we get a very high count rate, and that distorts our result. But if we isolate just the low count rate samples, we can take this part of the distribution and we can use that to calculate our density. We just take an average of just that portion of the distribution, and that gives us our density measurement. So this technique is what's referred to as the rapid sample algorithm. The process of dividing up the counts into bins like that, that's the rapid sample algorithm. You hear people talk about rapid sample density, you hear people talk about low count rate density. That's what they're talking about. It's the density that's calculated from the low count rate samples that have been isolated using the rapid sample algorithm technique. Now, of course, we have, as the name of the tool suggests, a third method, which is azimuthal binning. And this works in very much the same way as the AFR, which I showed you earlier. We divide up the borehole into 16 sectors. This is looking downhole. The numbering and positioning of these bins is exactly the same as we had previously for the AFR. And let's suppose we're in a boundary situation with high density on one side of the hole and low density on the other. We'll look at the count rate in the detector as the tool rotates and see how that changes with azimuthal binning. So as the tool rotates, we see some bins which have a high count rate and some bins which have a low count rate. Notice that the high count rate corresponds to a low density. That's the general rule of thumb with density tools. The high density formation up here corresponds to a low count rate. So there's like an inverse relationship between count rates and density. So what we can do is, once we've divided up the hole into those sectors, is combine bins into quadrants and use the counts that are gathered in each quadrant to calculate density values. So again, you'll hear people talk about bottom quadrant density, top quadrant density, left and right quadrant density, in addition to the image that you can get by simply plotting the bins themselves directly. So let's look at how the three different types of density that we have, the conventional, the rapid sample, and the azimuthal, how they each respond to a situation where we're crossing a boundary, because this is quite important and can make a big difference when we're evaluating a reservoir. The picture shows a situation where we have a high density formation on the top, a low density in the middle, and a high density on the bottom. The brown stripe represents the borehole, and the marks in the borehole here are where the boundary is first penetrated the first time, and where the boundary is fully penetrated here, and then again on the second boundary down here. On top of that, we're going to superimpose a density log. So this is increasing density is in this direction, to the right or upwards. And we're going to look at how each of the curves that we've generated, the conventional and the rapid sample and the azimuthal, how each of those changes as we cross these boundaries. Let's start with the conventional density, plotted in green here. The conventional density, if you recall, just takes all of the counts from around the borehole. It doesn't discriminate between them, it just takes a bulk average. And so when we're up here in our high density formation, it's reading correctly, it's reading the high density. When we start to penetrate the boundary, then we start to see a gradual drop in density, because it's averaging out some of the values from the high density and some from the low density. And it's not until we get fully penetrated into that low density formation that it reads the true density of that formation. And then going the other way, we see something similar, where as we start to penetrate into the high density lower formation, the density measurement starts to increase, and it's not until we're fully penetrated in that bed that we actually get the correct density. Now here is an example from a real well. We've got gamma ray over here, we've got some resistivity curves. The main thing I want you to look at is the density curve. This blue curve is the compensated density, the average compensated density, which is the conventional density measurement. Now from this, it's a little bit difficult to say where the boundaries are between the layers. We see some very gradual changes here between boundaries. There might be two possible low density beds. Certainly the gamma ray seems to think that's the case. But it's not very clear from looking at this exactly where the top and bottom of this zone would be. And remember that we need to know the thickness of pay zones if we're going to calculate the total reserves accurately. So we need to know where these boundaries are with some degree of accuracy. So let's look now at how rapid sample data behaves around a boundary. Here we have the case of a single boundary where we've got high density above and low density below. And let's set the tool rotating. When it's in the high density formation, it's just going to read low count rate, regardless of which direction it's facing. We're assuming here that there's no standoff change, that the borehole is engaged. In that case, you're going to get just a constant, or on average a constant value, low count rate value corresponding to a high density. When the tool moves to the boundary position, we see variation now. We see high to low count rates as the tool turns from facing the low density to the high density formation. Now this has nothing to do with borehole enlargement. As I said, the borehole is engaged. This is all due to just differences in density from one side of the hole to the other. But the tool doesn't know the difference, and so it goes ahead and runs its rapid sample algorithm anyway, and will preferentially pick the low count rate samples and use those to calculate density and ignore the rest. And those low count rate samples are coming from the high density, so it's going to tend to pick the higher density in this boundary situation rather than the low density. It's only when we get into the low density completely that the count rates are high, and they're constantly high, and the tool is going to give you a low density value that corresponds to that. So let's look at how that appears on a log. Here's our original log where we're crossing two boundaries, and we'll put the rapid sample data on top of that as well. So we start off with reading high density up here, and even though we're crossing the boundary now, the rapid sample algorithm is going to tend to preferentially pick the higher density until there's nothing else to pick but the low density formation, at which point it drops and starts to read the correct value in the low density formation. But it's only when it's lost all trace of the high density formation that it actually does that. As long as there's any of this high density formation exposed to the borehole, it will tend to pick that preferentially over the low density value. Coming down to the lower boundary, something the opposite case happens, where as soon as the borehole penetrates this high density formation, the rapid sample algorithm will preferentially pick that and continue to pick that all the way down. So what happens with the rapid sample is that it tends to overestimate the density, and it tends to preferentially pick the higher density formation in a case where we're crossing a boundary. So in the real log, this is showing the same log we showed before. If we superimpose our rapid sample density on that, we can see we get a very different result. Now this bed here is looking considerably thinner than it did before. This bed up here is almost disappeared, to be honest. There's not much of it left. So this gives a very different impression of the thickness of these beds. Now the question is whether that is right or not. It probably isn't, because, as I said, it's preferentially picking the higher density, which means it's excluding intervals of sand, which might otherwise be regarded as pay zones. So let's look now at the azimuthal data and how that behaves in this same situation. We've already got the conventional and the rapid sample on this plot. Let's add the bottom quadrant azimuthal data and see what that looks like. That's the red curve, where, remember, this is facing the low side of the borehole now. This is the bottom quadrant density. So the low side of the borehole is seeing high density up until about this point. And when the borehole starts to penetrate the low density formation, the bottom quadrant will see that straight away and will start reading low density on the low side of the hole. And when the low side touches the high density formation, it'll jump up again and show the higher density. Meanwhile, the top quadrant, which is the light green curve, shows similar kind of behavior, except this is now facing upwards. So it's showing higher density for longer before it switches over to low density. And then it shows the low density before switching back to the high density again. So it actually gives a very similar response to the bottom quadrant, except it's shifted in depth deeper down the well in this case. So let's look at what that looks like on a real log. If we add the bottom quadrant density, we get something very different from what we had before. Now we're seeing some quite sharp, clear boundaries. We've got one large sand, it looks like, and one smaller sand, nicely, sharply divided. If we add the top quadrant to that as well, the light green, which I hope you can see well enough, you get a similar response. It's not quite the same shape, but it's very similar. Again, showing two distinct sand lobes, whereas previously the rapid sample basically wiped out this top lobe almost. Now it's showing a much more distinct character, and the bottom lobe, the bottom quadrant, is showing a nice clear lower sand, which on the rapid sample looked a lot thinner. Now, there's one way to be clear about what you really have in this situation. Just looking at these curves, it's very confusing to know which one is which and to which one might be best. There's one way to get a much clearer picture of what's going on, and that, of course, is to use an image. Here I've got the density image plotted, and this is clearly showing our two beds. We've got a nice thin sand and a much thicker sand below it, separated by a thin shale. There's even perhaps a tiny little bit of extra sand or a thin streak perhaps on the top of this right here. Now, no single curve on here completely represents the complexity of what's going on. So that kind of brings to light the importance and the value of an image in understanding the situation. So be careful when you're looking at this data. You need to know how each of these curves is going to respond, how each one is going to look different, and be careful about particularly using the rapid sample data, because that does tend to reduce the apparent reserves, because it tends to pick shales, dense shales, rather than picking lighter sandstones. But there will be some cases where you don't necessarily need or want to use an image. We want to present what we regard as being our best density curve for a particular situation. In that case, what we recommend is that the bottom quadrant density is used in most cases where the well is deviated or in high angle situations. The reason for that is that the bottom quadrant is going to have the minimum standoff for the most part. The tool tends to lie on the low side of the borehole, so the minimum standoff is going to be from the low side. It also gives the most realistic indication of bed thickness, as we saw in the previous example. Although the exact position in terms of measured depth of a particular bed may be different depending whether you use top or bottom quadrants, the thickness of the bed is the main thing of importance in terms of evaluating the reservoir and evaluating the reserves. So bottom quadrant in most cases will give you the best from that perspective. If the well is almost vertical, or if the well is rough or enlarged, then quite often the rapid sample density will give you the best result. In the near vertical case, the rapid sample data will come from whichever side of the hole happens to be closest to the detectors at any given moment. It doesn't necessarily always come from one side of the hole, and so you're really depending upon the tool at least coming close to the formation some of the time in order to get a good, reliable measurement in those cases. But even in those cases, that you can sometimes have problems where you have a very large borehole that's near vertical and the tool simply doesn't touch the sides, in which case you're going to be struggling to get any kind of reasonable measurement at all. But for most applications, as I say, deviated wells, the bottom quadrant is preferred. For near vertical wells, then the rapid sample measurement is preferred. Now, the image that we get from the ALD is not purely for formation evaluation. It's also useful for more geological applications, in particular for helping us understand the structure that we're drilling through. In the same way that we can with the AFR resistivity image, we can also take the density image and use it to calculate formation dips and to identify the presence of faults, and also to use that information for geosteering decisions in real time. Now, the image doesn't have the detailed resolution that the AFR does. The resolution of the density image is maybe a foot or thereabouts compared with the inch or half an inch that you get from the AFR. But it still shows a lot of information, as you can see on this example, where we're landing a well horizontally. We're coming down, this is the TVD curve, coming down and leveling off horizontally, and we can see that as we're coming down we see these layers that we're cutting through until we finally land out parallel to the bedding down here, where we lose these sinusoidal features and just start seeing these kind of stripes down the log. That's where we're parallel to the bedding, which is a very useful indicator, especially real time, to help us understand where we are and how we're moving through the structure. This plot shows two images. They're actually the same image repeated. The second one just has the bed boundary pics, which come from Borehole Imaging Studio, and the corresponding tadpoles showing you the true dip and true dip azimuth in the right-hand track. Incidentally, I've used the same tadpole display to represent the borehole trajectory here. This is the inclination and the azimuth of the borehole. So inclination on a scale of 89 to 91, so that's 90 degrees right there, so that's perfectly horizontal, and we're drilling to the east, indicated by the tail of the tadpole. I should also mention that although I said we can calculate dip from the ALD image, we really need to be over about 70 degrees inclination, or strictly speaking 70 degrees relative dip, before we can be confident in the measurement that we make of dip from the density measurement. The uncertainties associated with the density and the fuzziness in the image which introduces uncertainty into the positioning of these sinusoids on the image. Those uncertainties all add up so that at lower inclinations, for example up here, where we have relatively low inclination, the uncertainties associated with these picks are greater than they are for higher relative dip picks like this one. So as a rule of thumb, we'd like to be over about 70 degrees to be able to pick reliably and to be able to calculate dip accurately for presentation to a customer. Now earlier I mentioned that the tool also produces something called the PE, the photoelectric factor. I'll just explain briefly what that is. Looking at the detectors that the tool has, it has two detectors, a near detector and a far detector. The detectors actually don't just count the gamma rays, they also measure the energy of the gamma rays. So rather than getting a simple count rate, we actually get a spectrum of energies. So this is count rate versus energy of the gamma rays that come into the detector. Now for the purposes of the density measurement, we just use this portion of the spectrum that's shown here, the relatively high energy end of the spectrum, because the count rate within that window is governed primarily by the density of the formation. Now there's another process which happens in the way that the gamma rays interact with the formation, and that process involves the capture of gamma rays. This is somewhat similar to what happens in the neutron with the capture from chlorine, except this is not anything to do with chlorine. This is just regular atoms in the formation. When the gamma rays have high energy, they will just tend to bounce off atoms and lose energy. Whereas when they get down into the lower energy range, it's possible for them to be captured. The process for capture is called photoelectric capture. I won't get into the details of what that means, but what it does is essentially reduces the number of lower energy gamma rays that we detect. You might expect the gamma rays, in fact, from a spectrum like this to kind of just pile up against the low end of the spectrum. As they lose more and more energy, you end up with more and more low energy gamma rays, so you might expect a curve that just kept on going up here somewhere. But in fact what happens is that the lower energy gamma rays get captured, and that reduces the count rate in this part of the spectrum. Now those gamma rays are captured by elements in the formation, and different elements are better or worse than other elements at capturing gamma rays. So there are certain elements which are very good at capturing them, and there are certain elements which are less good. So by looking at the number of gamma rays that show up in this window and comparing them with the number that we had in the density window, that ratio between the two windows, or the two count rates in the two windows, can be used to derive this thing called the photoelectric factor. And that photoelectric factor is an indicator of lithology. Basically, the factor changes with the elemental composition of the formation, which is directly connected, of course, to the type of lithology that that formation has. So there are known values of photoelectric factor which come out of this calculation, which are associated with particular types of formation. And as such, you can use this as a lithology indication flag. We don't necessarily need to understand the details of the physics, but it's just enough to know that we have a PE factor which can be associated with particular formation types. And this table shows a summary of some of the more common minerals and some of the fluids that are found in boreholes with their associated PE values. First of all, you'll notice that the heading of this shows that the PE is a unitless parameter. You may see on logs, older logs from Sperry and logs from competitors, that the PE factor is labeled with units of barns per electron, or B/E. We recently showed in a paper that that's not actually correct, that the PE factor should be unitless, and for the last couple of years Sperry logs have been using a unitless PE curve. But that doesn't change the values associated with them. So for example, in a quartz we would typically expect a value around 1.8, compared with a calcite of around 5. So that's, a clear differentiator between the two. Also, usefully, dolomite is significantly different from calcite. So in places like the Middle East, where we have a lot of dolomite and limestone layers intermingled with each other, the PE can often be used to discriminate between the two, where otherwise it might be quite difficult to tell the difference. There are one or two minerals which are very close to each other, so you have to be a little bit careful. For example, things like gypsum versus dolomite, they're very similar. Shale and gypsum, shale and dolomite are also very similar. So you need to have some care when you're interpreting the PE curve. It's tempting to just use it by itself, but it's better to use it in conjunction with other measurements just to sense check some of the conclusions that you're coming to. Notice also that some of the fluids that you find also have PE associated with them. Water is 0.3, salt water is quite a bit higher. The thing that really gets us, though, is the barite. Barite is a weighting agent which shows up in drilling fluids and has an extremely high PE. What that means is that in a mud system or drilling fluid which has a lot of barite in it, that can seriously distort the PE measurement from the tool. So you have to be careful about that. And in practice, heavier mud, which is weighted with barite, means that we probably don't have a usable PE value from the tool. It really only works best in lighter mud weights. So here's an example from the Middle East where we have a nice PE response. We have in the lower track gamma ray and caliper curves. We have resistivity curves in the middle. But up here is where the interesting part is, which is where we have the neutron porosity and density. And the black curve is the PE, the photoelectric factor from the density tool on a scale from 0 to 10. And you can see that in this section right here, we've got a value that's averaging around 5, which from the previous table would suggest a calcite or a limestone. We then see a rather erratic series of beds before it finally levels out at about 3, which would be an indication of dolomite. Then we get back into some limestone and then back into some dolomite again. Given that we are in the Middle East, and given that we know this is a limestone reservoir, that's not an unreasonable conclusion to reach. You can probably tell or infer some of that information from looking at other logs. Based on the separation between the density and the neutron, for example, you might be able to tell something about the formation. But there's also, of course, the risk that that could be due to changes in fluids rather than changes in the actual rock matrix. So the PE is a useful flag, a useful indicator. And in places like this, where we're not overly influenced by the barite in the mud, we can get a pretty good result. And it's a very useful curve to have on the log. So just to summarize on the PE, it's a lithology indicator. You don't necessarily have to worry about how it's calculated. You just accept the fact that it's an indicator of lithology with known values that are associated with different lithology types. What you do need to be aware of, though, is that it has limitations in terms of mud density. Typically, we would say that less than about 12 pounds per gallon mud, and you should get a reasonable result. More than that, and assuming that the mud is weighted with barite, which most muds are, above about 12 pounds per gallon, then you won't get a reliable measurement, most likely, due to the high PE of the barite. Now, the barite does actually have some benefit in that the PE image, the azimuthal PE image, because of its sensitivity to barite in the mud, means it's also very sensitive to standoff between the detector and the formation on the ALD. And that means that it's a good way to see changes in the shape of the borehole. So you can see washout, you can see breakout. Sometimes the PE image is actually the best indicator of those sorts of mechanisms in boreholes where you're looking for changes in shape. So bear that in mind. It's a useful indicator, even if in a case where the barite is so high in concentration that it messes up the PE, it might qualitatively still give you something useful on the image for the purposes of borehole shape interpretation. So I just want to finish off with the density by showing you a couple of example logs. This is a typical triple combo log where we've got a gamma ray and a ROP, this is a rate of penetration in this track, and HSI, which is the hole size indicator. This actually comes from the density tool. It's not from the acoustic standoff measurement. It's from the density itself. This is a byproduct of the rapid sample algorithm that I was talking about earlier, where we can estimate the standoff and therefore the hole size in the low count rate and high count rate bins from the rapid sample algorithm. Again, I'm not going to get into too much detail on exactly how that is calculated, but you can see there are big gaps in it, and the gaps are due to the tool not rotating. That value is only calculated when the tool is rotating. That's backed up by the trace in the center track, the depth track, which is the ALD tool face. That's the orientation of the detector blade relative to the high side of the hole. Where it shows an erratic response like this, generally means that the tool is rotating. Where it shows a more smooth response, like this interval, it means that the tool is sliding. This would be a case where we're drilling the well with a mud motor, an oriented mud motor, which allows us to drill the well without necessarily rotating the drill string. So in this section we're drilling while sliding, and here we're rotating again and sliding down here, although the data is a little patchy through that section. In fact, the hole size indicator is probably a better indicator of where we're rotating and where we're not. Over here you've got the resistivity, which doesn't look particularly interesting, but over here we've got the density, which is the rapid sample density, limestone porosity, and the delta rho, which I haven't really discussed here, which is a quality indicator for the density measurement, which indicates how much of a correction has been applied for standoff between the detector blade and the formation. Typically you want that to be small. In this case, what we're looking at is the interval where we're sliding here. So this orientation from the ALD tool face suggests that we're roughly minus 90 degrees or so. What that means is 90 degrees anti-clockwise from the high side. So to the left side, the tool is facing kind of the left side of the hole. And you can see intervals where we are getting a very, very low density measurement, like in here. And that's associated with a very large delta rho, the delta rho standoff correction. What that means is that that measurement is probably not reliable in that case, because the tool is facing not the low side, but to the left side of the hole, where the standoff could be quite large, and that's adversely affecting the density measurement. Where we're rotating, we get a nice, good, solid density around here. My suspicion, based on the fact that the gamma ray and the resistivity don't really change much through this interval, is that the density should really just follow a path through here rather than deviate to the low side like this. So this should be flagged up as unreliable data. The fact that the neutron also seemed to kick over, it's showing remember the neutron is on a reverse scale. This is on -15 to 45 scale. So it's wrapping round, it's going high, and it's going high because of the enlarged borehole. So there's lots of fluid in the borehole around the tool, which we're not correcting for. So the porosity reads higher than it should in that interval. So we know we're going through a washout, the density is adversely affected. And that's the sort of thing you need to look out for. Otherwise, you might be inclined to interpret that as a genuine formation response, which might lead you to suspect that it's a coal or something like that you've drilled through, some low density formation, when in fact it's just an artifact of the orientation of the tool through that interval. You can see down here something similar is happening when we go sliding again, that we're getting some rather erratic looking density results, which probably aren't realistic through that section. Finally, I've got a plot here which has an awful lot of information on it, and I'll try and explain what's going on. What this shows is a mixture of data, all of which came from the ALD. We've got, starting over here, we've got the density image. Next to that, you've got the PE image. This plot here is the a cross-section of the borehole that has been generated from the PE data. Next to that, you've got the delta rho, which I haven't, as I say, really covered in depth in this presentation, but it's an indication, again, of standoff, or how far the detector is from the formation, and how much correction has been applied for that. Over here, you've got bottom, top, left and right quadrant densities, which are all agreeing nicely with each other. So that's telling us we've got a nice gauge borehole, probably. A few other things on the plot. We've got a standoff from the acoustic standoff measurement on the tool. This is a tool that had an acoustic pinger built into it. And this is the cross-section of the borehole generated from that. And then over here we have various caliper curves which are generated from that acoustic standoff data. Now, the important thing to note, of course, on this plot is what happens around here. Here we had a case where we were drilling quite happily down to this point, where the ALD reached, and the bit was down at about this point down here, where the rig had to stop to make some repairs to the top drive. And they spent a couple of days, or 2 or 3 days, in fact, fixing the rig before they were able to get back and continue drilling. So in that time, the section of log, or the section of hole from here down to where the bit was left open, or the entire hole section was left open, but this section was left open and unlogged by the ALD. So when we came back in to log the hole and to continue drilling, we noticed this dramatic change in the image response, where we had these 2 bright streaks down either side, the left and right sides of the borehole, which shows up on the density, it shows up on the PE, shows up somewhat on the delta rho. The delta rho is kind of getting confused by this situation. What this is breakout. This is directional breakout associated with stress in the rock. When the hole was left open for a long period of time, it tends to collapse, and it tends to collapse in a certain direction based on the minimum stress direction that exists in the rock formations. So when we came back in, we found that the hole is no longer circular. The PE cross-section is attempting to show roughly what the hole shape is. It's certainly no longer circular. And here you can see the benefit of that PE being sensitive to the barite in the mud. It's showing dark values, which is a high PE value associated with that barite, which by itself isn't very useful, but qualitatively it shows you quite nicely where the enlargement is taking place in the borehole. Notice that the bottom quadrant density really doesn't change all the way through this section. That we're lying on the low side with the tool, and this central part of the image is where that bottom quadrant curve is coming from. And so it's still able to produce a good density measurement, even though we've got significant degradation in the borehole. Over on the left, we've got a bit of a mess, really, because the standoff, the acoustic standoff measurement, which is what's generating this image, really doesn't show anything meaningful. If you look closely at the image, you'll see this white stuff in the image, which corresponds to very small standoff, which makes no sense at all in this case. What's happening there is that the hole is so large in that direction, or the standoff is so large in that direction, that the tool is no longer able to measure it and just defaults back to a 0 value. So although there's some indication qualitatively there's something wrong with the hole, it's not at all clear looking at the acoustic standoff that it's actually what the actual hole shape is in that interval. You're better off looking at the density and PE, at least for a qualitative view of the hole shape, even though we can't get a quantitative measure of how big the hole actually is in that area.